right, getting into section 3 of chapter 13, looking at some work with some basic trig identities and using those to solve some equations. So looking at the first one, first note is that this identity, even though you probably just would know this one off the top of your head, and we dealt with this one in the first video, this is in your formula packet as well as this one. There is not a lot in your formula packet when it comes to trig identities. You get just a couple that are in there. So these are going to be the most commonly used. So these are the ones you got to be familiar with. So tangent we already know is sine over cosine. And we can see where that comes from right here. So this Pythagorean theorem identity, sine squared plus cosine squared equals 1. Again, keep in mind where that comes from. When you're doing things in radians, that's the idea of having a radius of 1. And so if we were to do just a basic Pythagorean theorem on this, we would do x squared plus y squared equals 1 squared. Well, remember that x is represented by cosine, y's are represented by sine, so it's like saying cosine squared plus sine squared equals 1 squared, and that's where this guy comes from. Of course, you can rearrange the terms in that formula, so could get sine squared by itself if we need to, could get cosine squared by itself if we need to, just depends on the question that we're working with. So if we wanted to use an identity to figure out something like this, so we're given that sine is 5 over 13, and we need to use that to identify what would cosine be and what would tangent be. There's a couple different ways to do this. One would be to do it the way that you're seeing here, where we just use the formula, and that's the one I'm going to go through. But I also see students at times just use a basic right triangle. If sine is 5 over 13, remember sine is opposite over hypotenuse. So if I just created a right triangle, so here's, let's say we're going to take the sine of theta. If I was going to do opposite over hypotenuse, then I would say opposite, so 5 over 13. And if I just used Pythagorean theorem, I would figure out that this leg is 12. And so now I could do things like cosine is adjacent over hypotenuse, so 12 over 13. Or you could say tangent is opposite over adjacent, so 5 over 12. And so you could do it with right triangles. You don't have to use the identity, but there's going to be cases where you really need the identity, so it's good to practice with it. Anyway, if I just plug in what was given to me, so we formatted it this way, since I know the sine value is 5 over 13. Keep in mind that when you have sine squared of x, that is the same thing as saying sine of x times sine of x. So you are technically squaring the entire function. And so that's why you can just do 5 over 13 squared. So if I do 1 minus 5 over 13 squared, and then I square root both sides, we're going to get our answer for cosine. And so that's what you're seeing down here for the cosine result. And then tangent, we're just using the other identity, and we're going to do sine over cosine. So we're going to do the sine of x here, so 5/13 divided by 12/13, and that's just going to give you the 5/12. Right here it says tangent of x is 7 over 4, and is a quadrant 3 angle. You got to keep in mind why they're telling you that. They're telling you that so that you get the signs correct on your answer, whether they're positives or negatives. If they tell you that it's in quadrant 3, so keep in mind that tangents are positive in quadrant 3. They're also positive in quadrant 1, and so they needed to tell you which quadrant we're working in here when we go to get our other answers. So we know this is all coming from quadrant 3. Based on your little acronym that we have here, we know that in quadrant 3, only the tangents are positive, so my other two values should be negative. So my cosine should be negative, my sine should be negative. But if we go back up to these guys, so again, we know tangent is sine over cosine. So if sine over cosine is equal to the tangent, 7/4, do a little cross multiplying here. If I multiply the cosine over, then I get this look right here. If I square both sides, then I'm going to get sine squared is now equal to 49 over 16 cosine squared. We know that based on our formula from here, So we're now doing a little substitution with the trig identity that you see up here. We know that sine squared is equal to 1 minus cosine squared. So we are now taking this equation right here. So we now have 49/16 cosine squared is equal to 1 minus cosine squared. So that's our new equation right there. Right here, if I add cosine squared over, so that's like adding 1 cosine squared to both sides. And that's going to give you this new equation that you see right here. And so now if we divide the 65/16 over to the right, you get to this look right here. Square root both sides. We're going to clean that up, get this look right here. Again, we're throwing in the negative because of what we talked about at the start of this problem. We can now sub this back in order to get our sine value. And again, we know that would be negative because of the quadrant that we are in. So using identities to solve some equations, dealt with this a lot in the last video. Keep in mind that this is the given domain. So two things about that. One is it's first in degrees, so you need to make sure everything you do on this problem is in degrees, including your answers. Also, we got to find every x value within one full circle from 0 to 360. So solving this equation, one thing you got to make sure you do is you kind of need one trig function to solve an equation. So right now, as it's written with two different trig functions, can't really solve it that way. So we have to take some step towards creating one common function. So the way that we did this in this problem was to divide both sides of the equation by the cosine of x. Those would cancel, and we know that sine over cosine is tangent. And so that gives us a new function that we see right here. Now we can do the inverse tangent of both sides. Remember, your calculator would be in degrees for this because of the domain that we see right here. And so if we do the inverse tangent of 2, we're going to come out with 63.4 degrees. Quick reminder that anytime you are solving these trig functions, in order to get all your other answers, you're always considering one basic concept here. If it's a sine function, I'm always looking up and down to get my solution. So if I had, say if I was solving a sine function and I had a positive y value, a positive sine value to here, then I would look here to get my other positive sine value. If we did cosine, we'd be working left and right because cosines are x values. So if I had a positive cosine value to get to here, then to get my other one, I would also have to go to the right to get my other answer. But when you are doing tangent functions go diagonally across the circle to get to each other. So in this one, when we got our 63.4 degrees here, we got to go across to the opposite quadrant and have the same reference angle of 63.4. So from 180, we would say 180 plus 63.4, and that's going to give us our second answer right there. So again, with this one, you got to have a common trig function in order to solve. So if we subtract the 2 cosine x over to the other side, divide both sides by cosine, then we can now get this look that you see right here. Divide the 3 over, and this is what we need to do the inverse tangent of in order to solve. I would have done it just a little bit differently than the way you see it right here in the notes. I just throw the negative into my calculator. So I would have said the inverse tangent of negative 2/3, and that's going to give me an answer of negative 33.7. So I would say, okay, from 0, I'm going to travel negative 33.7 degrees to get my first answer, which is right there. So if I did 360 minus 33.7, I get my first answer. Since it's a tangent function, I'm going to go diagonally across to get my other one. So this must be the same reference angle of 33.7 degrees. So now I'm going to do 180 minus 33.7 to get that answer. You got to notice the change in directions here for part B. They're still giving us a domain within one full unit circle from 0 to 2 pi, but now everything will be in radians because this is in terms of pi and radians. And also, we're not using necessarily 3 sig figs. We're going 2 decimal places. That's another thing you have to notice on a test for the change in directions. So solving this equation right here, again, you're looking to create a common function. As soon as you see the square, you got to be thinking of the Pythagorean identity. So I'm going to replace cosine squared with 1 minus sine squared, and that's going to give me the new equation that you see here. But now everything is in terms of sine, so now it's solvable. Distribute the 3, and you get to this stage right here, get everything onto one side, and it's like solving a quadratic equation that we have right here. So think of this as 3x squared plus 5x minus 2. And if we were to solve that by factoring, you would come out with this look here. Anytime you solve by factoring, you set each factor equal to 0 and solve it. So after setting the first one equal to 0, we get this look here. And we're going to do the inverse sine of 1/3 in order to get those solutions. I can also do this, but you have to notice you can't do the inverse sine of any function and come out with -2 as an answer. So this is an option we can reject. So just doing the inverse sine of 1/3, you get the 0.34. Remember, we're in radians right now. So if I got 0.34 represented by this angle right here, so remember this is about 1.6 because it's pi over 2. So this is about 1.6-ish. So 0.34 would fall within the first quadrant. Sine values go up and down. So because this was a positive 1/3, then I know I went up to get that answer. So this is a sine function, so I must go up again to get my second answer, and that's where this one's coming from. So if I do pi minus 0.34, I get my second answer. Right here, we're going, something to consider of reworking this formula right here. This should say y over x, not x over y. So if this said y over x, then I can multiply x over to here to get y by itself. And that would give you this statement that you see right here. So for a case like this, if we knew that we had an angle of 60 degrees, and so I can now say y equals x tan 60, right, then it gives me just a way of isolating y and getting a statement like this. Or if I know that y equals 3/4 x, then again I can replace y with x tangent. That would give you this look right here. Divide both sides by x, and we have 3/4 equals tangent of theta. Do the inverse, and you get the angle formed by the line and the x-axis. And so again, this was just all about working with a line like y equals mx plus b, where b is 0 because it's passing through the origin. For the rest of these notes, there are two formulas that you have within your formula packet for double angle formulas. So one is the double angle formula for sine, the other is the double angle formula for cosine. These are both in your formula packet, so make sure that you notice that those are in there and know where to find them. A couple things that we're going to go through, but I'm going to run out of time in this video, so I'm going to create a second video here to work with the formulas, or the solving the equations down below, because that's just a really important concept for this chapter that you got to be able to do. And so these are the two formulas you got to take note of. So real quick on these, if I wanted to find some other values like this, so if I had the sine of 2 times some angle that I have right here, well, if I know that the sine of x is 1 over rad 5, well, if I square both sides, then I get the sine squared of x is equal to 1/5. I can now replace sine squared with 1 minus cosine squared, and then go ahead and go on to solve for the cosine value. So that's what you're seeing going on with this one, and we get that cosine value. Now that I know cosine is 2 over rad 5 and sine is 1 over rad 5, I can now plug those into the double angle formula for sine that you see here in order to solve. And then real similar with this one, if the tangent of some angle is 6, well, we know tangent does opposite over adjacent. So think of this as 6 over 1. So if I identify an angle, tangent is opposite over adjacent, and now I can use Pythagorean theorem to get the hypotenuse. And so now I can identify my trig ratios from that triangle. So here would be my sine value, here would be my cosine value, and now I have all the information I need to plug into the double angle formula for cosine that you see right here in order to get my solution. So I'm going to create a continuation of this video here to go through the rest of the notes of solving these equations, but I want to spend a little more time on these. So make sure you pull up the second video on this for this lesson continued.